Hello everyone, my name is Yunfei Lin. I'm a researcher in the Cyber Physical Systems Group at the Technical University of Munich in Germany. I'm presenting our paper, Sampling-Based Trajectory Repairing for Autonomous Vehicles. The co-authors are Sebastian Meyerhofer and Matthias Adhoff. This work is funded by German Research Foundation and BMW Group within the Cartoon project. There are several reasons for proposing the idea of trajectory repairing. First, ensuring the safety of autonomous vehicles is a challenging task, when correctly predicting other traffic participants' behaviors are non-trivial, especially in partially unknown, complex, and dynamic environments. Another reason is that machine learning-based approaches have been widely used in motion planning problems of autonomous vehicles. However, they often lack safety guarantees. It's possible that no safe action is found in the remaining time prior to a collision. The last reason is, so far, there exist no motion planning algorithms that outperform the others in all traffic scenarios. In complex cases, the planned trajectories may not consider all traffic rules or they are physically infeasible when finding solutions under severe real-time constraints. As replanning the complete trajectory would be computationally expensive, we present a novel approach for repairing invalid trajectories. As shown in the sketch, the initial trajectory of the eagle vehicle collides with the most likely trajectory of the black vehicle. In our approach, to avoid the collision, the section of the initial trajectory before the so-called cutoff state stays unchanged, and the section after cutting off is repaired. That is, the repair trajectory section begins from the time of the cutoff state. To achieve this, we first detect whether an initial planned trajectory disobeys traffic rules by the traffic rule monitor. If the answer is yes, we use the time to react to determine the cutoff state. Then quintic polynomials are generated as a high-level reference path starting from the cutoff state to reach the goal region. Based on the reference path, the proposed sampling-based algorithm repairs the section of the invalid trajectory starting from the cutoff state. After obtaining the repaired trajectory, directed executable motions are sent to the control layer. Next, I will explain the sampling-based trajectory repairing algorithm in detail. The first part is the detection of the cutoff state by calculating the time to react. The time to react is the maximum remaining time for the last possible evasive maneuver. We can obtain the time to react as a maximum of time to brake, time to steer, and time to kick down, which are the maximum remaining times to execute evasive braking, steering, and accelerating respectively. We can see the illustration in the figure below. In this work, the time to react is approximated using a binary search algorithm with predefined evasive maneuvers, which is anytime capable. The next step is to generate a reference path starting from the cutoff state to reach the goal region. To explore the state space and to guide the sampling process, we generate a set of paths through quintic polynomials. The polynomials are generated in a freenet frame, where the movement of vehicles is decoupled into a longitudinal motion along the freenet curve and the lateral motion perpendicular to it. The freenet curve is the shortest path through the road network from the cutoff state to the goal region. We can use, for example, discharge search algorithm to create it without considering other obstacles. Afterward, we'll use a series of avoidance points to generate the polynomials and to cover possible homotopy classes. Two paths are said to be in the same homotopy class if they can be deformed into each other without passing on or looping around obstacles. The avoidance points are shifted laterally from the point where a traffic rule is violated for the first time, such as the first collision point with the obstacle as shown in the right figure. In the end, we transfer the polynomials from the freenet frame to the Cartesian frame. According to the predefined cost function, we choose the collision-free and resolution optimal one as the reference path. To repair a section of the invalid trajectory starting from cutoff state, we extend the closed-loop rapidly exploring random tree algorithm, which is abbreviated as CL-RRT. RRT algorithms have been shown to be effective for solving trajectory planning problems in complex configuration spaces. In the original CL-RRT, an RRT is combined with closed-loop controllers, which enables application to vehicle with complex, nonlinear, and unstable dynamics. However, its sampling strategy may still lead to high computational costs, since no homotopy information is utilized. And the usage of the steering angle as a lateral input leads to the jerky motions of the ego vehicle. To solve this and utilize reference paths, we propose informed CL-RRT algorithm, which extends the CL-RRT regarding three aspects. The first one is the sampling strategy. To shrink the planning problem to subsets of the entire domain, we adopt a sampling method that generates samples following a Gaussian mixture model. The black crosses denote the centers of the Gaussians. The red colored bars of the figure below shows the contour lines of the probability distribution. As a result, the samples are located in the vicinity of the reference path. The second aspect is trajectory creation, which allows a forward simulation of the vehicle to create a feasible state trajectory along a given target line. In the steering controller, we use the steering velocity instead of the steering angle as a lateral input to avoid jerky motions. The pure pursuit controller provides a desired steering angle, and the PI controller seeks to minimize the difference between actual steering velocity and the desired value. With this, the vehicle can be well controlled to follow a given target line in the lateral direction. For velocity tracking, we use the PI controller as the original CL-RRT. Additionally, the acceleration variation needs to satisfy the jerk limit to enhance comfort. The last aspect is the tree expansion. Similar to the original CL-RRT, we obtain samples until a given time limit is reached and return the trajectory with the minimal cost. Each state of the previously created collision-free trajectory is converted into a node and added into a tree. But we only check the possibility of reaching the goal region when the orientation of the collecting line between the node and the goal sample is located in the desired interval. When the condition is satisfied, we will forward a new target line connecting the node to the goal sample to create a state trajectory. To demonstrate the benefits of our algorithm, we evaluated with traffic scenarios from the Common Road benchmark suite, which provides us a means of evaluating and comparing our algorithms. What's more, the polynomial sampling-based motion planner is used to generate initial trajectory. The first scenario is a rural terrain road. In this scenario, two static obstacles block the ego vehicle's driving lane, creating a narrow passage. The initial planner shrinks the size of the obstacles to first explore the state space with low computational effort, which relaxes the planning problem but generates a trajectory that collides with the obstacle B2. The time to collision is computed as 2.4 seconds, and the time to react is 2.0 seconds, which is calculated by simulating different evasive maneuvers. Since the collision happens close to the goal, it's more efficient to repair a trajectory instead of replanning a complete trajectory from scratch. After implementing our repairing algorithm, safe, comfortable, and stable motions are generated to avoid a collision in real time. We also compare our approach with the A-star search algorithm using motion primitives. The motion primitives are generated by a so-called constraint graph, which consists of all possible trajectories starting from the same initial state under the same physical boundaries. The graph search process starts from a cutoff state. Different from the A-star search algorithm, our approach doesn't need to consider a discretization of the state space, and we generate feasible trajectories without selecting them from a large set of candidates. The proposed algorithm works in urban scenarios as well. The ego vehicle passes through a T-intersection along with 3 other vehicles. Due to a time limit and the complexity of the T-intersection, the initial planner fails to provide a safe trajectory to reach a goal region, and the intermediate plan trajectory enters opposite lane. By making reasonable use of an intermediate plan result, we efficiently obtain a repair trajectory which is collision-free and physically feasible respecting the right-free rule. Also, the smoothness of the repair trajectory is first ensured by interpolating a reference path. Regarding the computation costs, we compare the computation times of our approach with those required when replanning the completed trajectory. One repairs the trajectory from initial state using the informed CL-RRT, which is denoted by repairing from the initial state. Another one replans the completed trajectory using a polynomial sampling-based planner, which is denoted by replanning. We can find out that our approach has a significant advantage in computational efficiency, particularly when generating first safe and physically feasible trajectory with a cutoff state and a CL-RRT. In summary, we present a sampling-based trajectory repairing algorithm for autonomous vehicles, which reuses the initial planned but invalid trajectory based on criticality measures, that is, the time to react. Our approach is also computationally efficient since we separate the repairing algorithm into a hierarchical structure, that is, a high-level and a low-level planning problem. The reference path determines the chromatopy class, and the informed CL-RRT generates comfortable, stable, and directly executable motions for the ego vehicle. As future work, we will compare results with repairing a trajectory using optimization-based approaches such as MPC-based planner. Also, we consider only scenarios with collisions in this work, but our approach can be easily extended to other types of trivial rule violations using a trivial rule monitor, such as keeping a safe distance to preceding vehicles. Thanks for listening. If you have any questions, please feel free to contact us.